In this video, we're going to talk about the relative strengths of intermolecular forces, which is the final video of the intermolecular forces set. We're going to compare the strengths with similar molecular masses, and we're going to talk about the properties that arise from these different types of force. First of all, we're going to talk about the hydrides. Now, we have a graph here which has boiling point and it has number of electrons down the bottom. Okay, so electrons is going up in that direction and boiling point is going up in that direction. If we look here and we have all of the group 4 hydrides, we've got methane, first group 4 hydrides going up all the way to tin hydride at the top. So that means all of these are not in Knoth-Clabrel, therefore they have similar electronegativity, and so this must be London dispersion forces. And London dispersion forces get stronger if the number of electrons go up. So therefore that makes sense. We then go to the next one, we can see the general trend again, okay? And that general trend is up, and that is because there's no difference in electronegativity here, and therefore London dispersion forces, and the electrons are going up, and therefore they're getting stronger. Now, the thing to mention is this pH3. This pH3 is a bit of an anomaly, and we will mention it in a question coming up next. pH3 has a slight difference between electronegativity of hydrogen and itself. So P has a slight difference in electronegativity to H. Okay, but you can't really see a big difference though in the data, but it has got a permanent dipole, a bit of an anomaly. Now let's just jump up there to ammonia. Now ammonia, we know from the previous video that ammonia has hydrogen bonding, and it generally has one hydrogen bond. Okay, and then we go there to hydrides of group 6. So we've moved up to group 6. We've gone group 4, group 5, group 6. And then we're expecting our next hydride of group 6, which you haven't put on, is water. So when you look at that, you can see water is all the way up there. Now if we then put the next one on, which is group 7, okay, so we've got group 7 hydrides again, we can highlight a few things. First of all, if you look here, water, HF, NH3. All of them have hydrogen bonding, and notice all of them have a much higher boiling point than the other hydrides in their group. So the other hydrides in their group are down there, and then it jumps up, okay? Now, if you then look at the 3 molecules, you can say, right, that has 2 hydrogen bonds. Again, from a previous video, we know it has 2. We know that HF has 1. We know ammonia has 1. But we also know that HF, well, F is the most electronegative because it's Knoth, and it goes up in order of Knoth. So NOF, N is the least electronegative, oxygen is the next electronegative, and then F is the most electronegative. So that makes sense that HF has a slightly higher boiling point because F has a bigger difference in electronegativity than N to H. Now the reason water is all the way up the top is because it has 2 hydrogen bonds where the other ones have 1. Okay, so, but the boiling point of all of these is way higher than their actual hydrides, again because of hydrogen bonding. Now, this means that we can go for a general rule. The general rule is that hydrogen bonding is stronger for molecules with a similar molecular mass. Okay, only for similar molecular mass. Really important to highlight that point. Similar molecular mass. Hydrogen bonding is stronger than permanent dipole-dipole, which is stronger than induced dipole-dipole forces. And that means you would expect something with hydrogen bonding to have a higher boiling point and melting point than one with permanent dipole-dipole, than one with induced dipole-dipole. But that only works if they have, and I say it again, similar molecular masses. Really, really important that you recognize that. We're now going to move on to comparing intermolecular force strength, okay? And we're going to explain the trend in melting and boiling points of the following molecules. Before we do that, let's go over an exam tip. The exam tip is to identify the types of intermolecular forces first. So if you ever do this, you ever got any molecules in front of you, look at them and say, right, what type of intermolecular forces do I actually have? Okay, and then try and compare the relative strength of those. Remember, our relative strength with relatively similar molecular masses is going to be London dispersion forces, then permanent, and then we've got hydrogen bonds. Remember, everything has London dispersion forces, everything has the electrons flying all over the place, and you get that unequal distribution of charge. It's just the permanent ones are stronger and the hydrogen bonds are stronger. So let's look at our molecules. So we've got fluorine, pH3, NH3 and H2O, and it's normally includes one of these with something else. So it's really good to know these examples. First of all, fluorine. Let's look at the type of intermolecular force. It is the same electronegativity, therefore there's no dipole, therefore that's definitely London dispersion forces only. We then go to pH3. pH3 is a kind of exception. It's one of those ones they try and put in, they're not very nice, and then try and put in an exception every now and again. Okay, and that one has differing electronegativity. It's not in Northcliffe, but so it's just an example you need to remember of a molecule. pH3 has got differing electronegativity, therefore has got a permanent dipole, therefore we've got permanent dipole-dipole attractions. Now they're slightly stronger than London dispersion forces because they've all got relatively similar molecular mass, and therefore you have a higher boiling point and melting point. We then have N bonded to a delta plus hydrogen, which is hydrogen bonding, and therefore one lone pair, 3 delta plus hydrogens. The smaller number is 1, so therefore on average there'll be 1 hydrogen bond per molecule. Okay, and then we have oxygen bonded to a delta plus hydrogen, hydrogen bonding again, 2 lone pairs, 2 delta plus hydrogens, therefore 2 hydrogen bonds, which means we have 2 hydrogen bonds versus 1 hydrogen bond, and also oxygen is more electronegative than nitrogen. So basically we've got a trend going down where the forces are getting stronger. So if you're answering this question, you have to say the relative strength of the forces is getting stronger, okay? And you have to detail all of those forces like we have done. And then you have to say that means that it takes more energy to break those forces, okay? And then you will have answered your question. So now we're going to move on to another multiple choice style question which throws a bit of a spanner in the works and tries to confuse students. So let's make sure we can explain it. Which of the following compounds has the highest melting point? And we've got 3 different compounds. And we will do exactly the same as we've done in the previous one, and we try to identify the intermolecular forces. So we do that through the dipoles. And let's put the dipoles on. Okay, so we've got there, and lastly, let's put the charges on. And that's where you might be surprised. So if we look here, there is an O bonded to a delta H. An O bonded to a delta H means that that has hydrogen bonding. We have this one. It's got a C bonded to an O. There's no delta positive hydrogen, therefore that's permanent dipole-dipole. But this one, yes, there is a dipole here, which we haven't drawn, okay, which is delta plus and delta minus. But more importantly, down here, there is an ionic bond. So I want to discuss the words bond versus force. A bond is much, much stronger than a force. So it is hugely stronger than a force. Okay, a force is down here in terms of strength. So when we're talking about relative strengths of forces, we're talking about down here. Forces, we're talking about, so bonds, we're talking all the way up here. Forces down here, bonds up here in terms of relative strength. So when we're comparing these, straight away, as soon as I look at that and I see there's an ionic bond, that means that has the highest melting point because it is the strongest attraction. Bonds are much stronger than forces. So therefore, the highest melting point and boiling point is going to be C. Now, if we do it in order, we can see that A has hydrogen bonding, B has permanent dipole-dipole, so the lowest melting point is going to be B, then it's A, then it's C because of the ionic bond. So look for an ionic bond because it can happen, the examples can be given. Now we're going to talk about the anomalous property of water resulting from the hydrogen bonding. So we have liquid water here, and the first anomalous property that we have is the fact that the boiling point of water is so high. We've already explained that in this video, but let's just go over it again. You've got hydrogen bonds forming as the molecules slide past each other. What I'll also notice is that the molecules are quite close to each other. So they're quite close to each other, and because they are quite close to each other, okay, they form the bonds and then they break as they flow past. But they're all disordered, randomly ordered, okay, and quite close. We then go to ice, very much different, a fixed structure, okay? A fixed structure, and they call it an open structure because it's literally forces and bonds. They call it an open structure, but you can see here that there are bonds and there are forces. So basically there are 2 hydrogen bonds per oxygen, okay, and they are fixed in position. Now, that means essentially you have 4 bonds, 2 hydrogen bonds and 2 covalent bonds. And that means if you've done your shapes, 4 bonds, 4 bonding pairs essentially, is tetrahedral. So we call it a kind of open tetrahedral structure in ice, solid water ice. So let's apply that to our questions. So why does water have a relatively high melting boiling point? Well, it's because it has those 2 strong hydrogen bonds that take a lot of energy to break. Why does ice have a low density compared with water? That's because it has this open tetrahedral structure, spaces out the water molecules, they get much further apart, and hopefully you can see this from the diagram over here. Okay, and so ice is less dense than floats. So let's look at this in a pictorial fashion. And look at the liquid water. Liquid water is like this, and then we've got our dipoles that are coming, and you can see these strong hydrogen bonds, but you can also see they're very close to each other, okay, very, very close to each other. Whereas we look at solid ice, let's put all those dipoles in again, and you can see the iceberg is floating on top of the water. That means the ice is less dense, and you can look at the space between the water molecules, look at the lack of space here, and so you can see that this is more dense than this. And the density of water is affected by the hydrogen bonds because the hydrogen bonds pull those water molecules close together and therefore increasing the density of the water.